Welcome. So far, we have discussed digital control systems or discrete time control systems, in which we have discussed all the first three units, where we have discussed the various types of digital control systems, the Z transforms of digital control systems, applied in digital control systems, the controllability, observability, the reachability, whatever that are required in the state space analysis. All these things we have discussed so far. And in this unit 4, we are going to discuss the design of control systems in discrete time, for discrete time systems, and in which we will be discussing the topic here today. It is design using pole placement technique. Using pole placement technique, or you can also call this pole placement as pole assignment. Pole assignment technique. That is, at times we will be required to change the position or location of poles so that it can the system can become stable or unstable, whatever required, or an unstable system can be brought to a stable region, right, based on the location of poles. Therefore, you can call this as pole placement or pole assignment technique. For this, we are going to consider a linear time invariant discrete time control systems. A very linear time invariant discrete time control systems, you can just give a statement like this: x of k plus 1 is equal to g into x of k plus h into u of k. You know that x of k is a state vector and it is an n vector or n by 1 vector at kth sampling instant. At kth sampling instant, and u of k is also an n vector, or it is a input control vector, or at kth sampling instant, right. So, and g and g is an n by n matrix, and h is an, again you can say this is, if this is n by 1, this is n by n by 1, and this is, for example, if it is an m by 1 vector, you can also call this as then n by n. Or if u of k you consider it to be a scalar, it can also be called as n by 1, and since u of k is a scalar, it can be treated as 1 by 1, right. So h is an n by 1 vector matrix, right. So based on these things, we will try to see that whether the system is completely state controllable or not. If here, for pole placement technique, we require the system to be completely state controllable. This linear time invariant system is required to be completely state controllable. State control. For example, let us say that x of k plus 1 is equal to g, x of k plus h u k is completely state controllable. What does that mean? It means that all the state variables are measurable and they are available, and these state variables are available for feedback. Right. So the state variables, when this system is completely state controllable, it means that the state variables are measurable. All the state variables are measurable. No any state variable is not non-measurable, and they are available for feedback. Feedback can be easily considered with here. So with that in mind, you can say that, for example, u of k is equal to minus k into x of k. X of k is our state variable, which are all measurable and available for feedback, and k is our state feedback gain matrix. We will define this type of matrix, which is we should find out k in such a way that u of k is equal to minus k into x of k, and if you substitute that in this equation, you will be getting the pole placement technique in this. This is called pole placement. So that is, if this system is completely state controllable, which means that state variables are available for us for feedback, then the feedback which you are considering from x of k is to input. Feedback is going from output to input, and here output is our x of k in this case. For example, let me draw this diagram in here. Let me say we are having, or let me draw it here. X of k plus 1 is equal to g x of k. For example, let me say we have x of, I am drawing double lines because it is a vector. X of k plus 1 is, if I apply z inverse I, then I am bound to get x of k here. Right? Inverse Z transforms of x of k plus 1 is x of k, and here, okay, now that equation gives us, what is this equation? X of k plus 1 is sum of g x k plus h u k, right? H, I have written here h, and I will consider u of k as a scalar quantity, scalar input, right? U of k. So that is why a single line, double line indicates the vector and single line indicates a scalar. Then h u k is given, therefore I need one more here. What is it? I require g x of k here. When I am going to draw g x of k, g into, this is x of k for, right? When this is x of k for me. Okay, so this is our equation. Now we have considered a feedback u of k is equal to minus k into x of k. This is our gain matrix or feedback gain matrix. Feedback gain matrix k. Therefore, this u is nothing but minus k into x of k. X of k is here for us. X of k is here. Therefore, I can have this. Now this is our system. Okay. Now if this system, if this linear time invariant system is completely state controllable, then this feedback is possible, is what we are trying to see in this design using pole placement technique. Okay. Now with this in mind, we are going to see what are the necessary and sufficient conditions for this system to exist like this. To find out k is the feedback gain matrix. So it is in the design using pole placement technique, mathematically what we say is finding out gain k, gain matrix k, to place the poles at the desired locations. So k must be found to place the poles or closed loop poles in desired locations. Wherever required, we wanted to place these poles in the desired locations. So for that to happen, what is the value of k matrix? That is what we are going to see in design using pole placement technique. Right. So this is a design control systems, discrete time control system, what we are going to do. Right. So with this in mind, we are going to see now what is the x of k plus 1 for us? It is g x of k plus h u of k, and u of k is equal to minus k x of k. Now when I substitute this here, x of k plus 1 is equal to g into x of k plus h into u of k is minus k xk. Therefore minus h into minus k into x of k, where you can say that g minus hk is our x of k. This is our x of k plus 1. Okay, G minus HK. Now G minus HK is the characteristic equation. Characteristic equation can be obtained from this G minus HK. Now we are going to see what is the necessary and sufficient conditions. Necessary and sufficient conditions for the placement, for the poles to be placed at desired location by finding out gain matrix K. Now what is the necessary and sufficient conditions here? For us, we say that the necessary conditions for this pole placement to happen, what did we say? The system should be completely state controllable. Okay, now this is our first thing. For example, let us say system is not completely state controllable. System is not completely state controllable. So now let us keep this equation in mind. This is G minus HK into X of K, which is a characteristic equation. Now we will see the step by step. We will go and see what is the necessary condition for the necessary condition. We will derive the necessary condition. Now what is the necessary condition? For the system to be, for the poles to be placed at desired locations, the system, the linear time invariant system must be completely state controllable. Now to prove this, let us say the system is not completely state controllable. Not completely state controllable. Now if it is not controllable, what is the condition for us here? The controllability matrix QC. What is controllability matrix? H, GH, G square H, G power n minus 1 H. The rank of this matrix QC must be equal to n for the system to be controllable. But if it is less than n, Q, which is less than n, where n is the order of the system which we have already designed, which we have already considered, x of k plus 1 is equal to j x k plus h u k. Right. The controllability matrix, if its rank of the matrix, rank of QC, rank of QC matrix is this, is equal to Q, which is less than n, right? Then it means that there are only Q number of linearly independent column vectors. Q number of linearly independent column vectors, and for those, what are they? I will consider them to be F1 bar, F2 bar, FQ bar. Q number of linearly independent column vectors. And what are the remaining n minus q number of linearly dependent column vectors? And let us choose those matrices to be, vectors to be VQ plus 1 bar, VQ plus 2 bar. They are vectors, that's why I am putting a bar sign there. Right. So n minus q type number of vectors which are also of this sort. Now let us choose P, matrix P, which is a transformation matrix. A transformation matrix P in such a way that, in fact, we will choose these vectors VQ plus 1 because we already have these vectors, right? We need to choose these vectors in such a way that P, which is the transformation matrix, is nothing but F1 bar, that is a vector, F2 bar, column vector, FQ bar, right? And we add this Q plus 1, V, Q plus 2, Vn bar. Right. So this is the transformation matrix which we have chosen here. Okay. Now with this in mind, again we can say that we have these equations where we are having G minus HK. G minus HK is our the matrix whose transfer function will be considered, whose characteristic equation can be obtained by Zi minus G plus Hk. Gi minus G plus Hk is equal to 0. Right. Now with this transformation matrix, and we should be able to find out another characteristic equation from after applying transformation to the existing system. Now what is the existing system for us? We have considered the system x of k plus 1 is equal to gxk plus h. We have considered the system g x of k plus 1 is equal to g x of k plus h into u of k. Now when this, let us choose the transformation matrix in such a way that x of k is equal to p